हाँ वही इसको छोड़ और ये थोड़ा हाँ कुछ नहीं हुआ
Good evening, everyone. I'm Rahul Chaudhary. I'm a PMR of PhD scholar from IIT Madras, and this is live problem solving session for the week 5 for the course EMI, EMC, and Signal Integrity, taken by Professor Amitabha Bhattacharya from IIT Kharagpur. So let's start today's session. I hope I'm audible. If you have any doubt, you can unmute yourself and ask me. Or if any point of time, if you are not able to hear me or any issue is there, you just please let me know. So today we'll start with a question that we have solved previous week session. So the question was, which of the following condition is desirable for the peak detector? So one student asked like why the answer was option C. Why the correct option was option A, not option B. So the problem is, if you consider a regular peak detector, definitely the correct answer in that case should be, we want the time should be less, the time constant should be less than should be greater than t in an ideal case for a regular application. But here what we are talking about is in terms of EMI EMC testing, and our aim is not to detect the regular peak of a signal. If there is a normal signal, yes, we can use a regular peak detector, but here our aim is to find these spikes, periodic spikes which are coming in the signal, which are unwanted signals. We don't want these spikes, and these spikes are like they appears for a very small time. The time period is very small and high intensity. So that's why so first I will start with the basic of what peak detector is. So the correct answer was same. There is no change in the answer. I am just explaining it again because in last session there was some doubt regarding that. So the correct option is still same, that T should be greater than the time constant RC. So first of all we'll start with how a peak detector works. How a peak detector So peak detector, what is a peak detector? It is a electronic device. A peak detector captures and holds the maximum value of an input signal. So peak detector captures and holds the maximum in the sense peak of a signal, as a signal of peak value of a signal. So if I draw one circuit diagram, a simple circuit diagram for a peak detector, it looks something like this. So there is this PN junction diode and a capacitor to hold the output when the signal is in negative state, and a resistor. And this part is grounded. Just a second. So those who have joined just now, we have just started the session and we are solving a question from the last week session. So because there was a doubt regarding why the correct option in this question was not option B. So the question was, which of the following condition is desirable for a peak detector? So if this question was from a course called linear integrated circuits, definitely the correct option is B in that case, because there our aim is to capture the peak perfectly for a periodic signal. But here the aim is different. Here our aim is in terms of EMI EMC. We want to find out the peaks, we want to capture the peaks of the transients or the spikes that are coming. So this is a regular signal, just one sinusoidal signal for example, and if some peaks are coming, something like that, these are spikes which are unwanted. So those are the things which we want to capture, and this capital T is the period of the spike, not the period of the signal. So we started with the discussion on how a peak detector works. So it's just I will just go through a brief overview of how a peak detector works. So a peak detector captures and holds the maximum or peak value of an input signal. So this is what a peak detector, a simple circuit diagram for a peak detector. It consists of a PN junction diode. So I'm denoting it as D, one capacitor and resistor. And from here we are giving this V in, and from this side we are taking out the V out. So I expect you guys will, if you have any doubt, you just stop me in between and please ask me. You can unmute yourself if you have any doubt. So the main components in a peak detector are, we just seen, sorry, main component of a peak detector. First one is diode. So we have denoted this as D in the circuit diagram. So what this does, this diode does is, it allows current in only one direction. So current flows through a diode when, if it is in forward biasing. So it allows current in only one direction. And then there is a capacitor, which we have denoted as C. It stores the peak. What the capacitor does is, it stores the peak voltage. and third component is a resistor. So you can see some circuit diagrams where this resistor is not present. So this resistor, what it does is provides the discharge path. Resistor, what it does is provides the discharge path. So now there are three phases in a peak detector depending on the signal. So first is the charging phase. Suppose this is our input signal, a sinusoidal is given as an input. Let's say this is one f of t and t. So this is our input. So the first phase is the charging phase. In this phase the diode is in forward bias and the capacitor starts charging. Charging phase. I can just write it as case 1, case 2, case 3. So this is the phase 1, where what happens is when the input voltage rises, because if you see this point, the input voltage is rising here, and then comes the peak. That is the second phase. So in phase 1 what happens is when input voltage is rising, or when input voltage rises, so what I mean by saying that the input voltage rises is the input voltage is greater than the voltage drop at capacitor and voltage drop at the diode. So it is increasing every time. So if I'm talking about in time period, let's say just a millisecond before, the voltage was something like this, and then just next time period it increases, means this is the increasing phase. So definitely the voltage here is more at this instant of time than this instant, right? So if it is rising, that means the V in is greater than Vc plus Vd, where Vc is the voltage drop at capacitor and voltage drop at diode. So the diode becomes forward biased. Diode becomes biased and the capacitor charges rapidly through the diode. Now since the current is passing through it, and the capacitor charges because the diode is in forward bias. The capacitor charges rapidly through the diode. So if this our time constant tau, which is given by RC, is small, ideally this is small, and immediately our Vc becomes V peak. It becomes quickly. So ideally that's what we want in a regular peak detector. And the second phase is when the voltage, this V in comes here. This is the peak, right? This is the peak voltage. So at peak what happens? At the highest point of the signal, capacitor stores the maximum voltage. So at the highest point what happens? Capacitor stores the maximum voltage. Now this is the maximum voltage. Beyond this, because this is the peak of the voltage, input voltage, so capacitor can't get a voltage above than that. So this is the maximum voltage that the capacitor stores, and diode begins to turn off when input starts falling. And just after the peak, what happens is now the diode goes into the reverse biasing. So diode starts, because after this next instant, if you see here, so after peak the voltage starts dropping. That means this condition won't be valid after the peak. What happens then is V in will be less than Vc plus Vd. So the diode begins to turn off when input starts falling, and the third phase is falling input voltage. So just after the peak, the input voltage starts dropping, falling input voltage. So when the input decreases, what happens is, when the input voltage decreases, diode becomes reverse biased. And capacitor is isolated from the source. Now since there is no flowing of the current, because there is no voltage drop in the diode now, because it's in the reverse bias, the capacitor is isolated. That means the capacitor is not charging anymore. Just a second. So those who have joined just now, we are just discussing one question where which of the following condition is desirable for a peak detector, and we are discussing how a peak detector works. So that peak detector consists of a diode, capacitor and resistor, and there are three stages of in a peak detector. The first is the charging phase, where the diode is in forward bias. At peak, at the highest point of the signal, capacitor stores the maximum voltage and diode begins to turn off when the input starts falling. And in phase 3, falling input voltage, when the input voltage decreases, diode becomes reverse biased and capacitor is isolated from the source. Isolated from the source. Now in this stage, what happens is the capacitor slowly discharges through the resistor, which is given by Vc voltage, which is now function of time, voltage drop at the capacitor. Since it is not charging, it is discharging now. Starts with the peak voltage and it degrades with e to the power t by rc, where this rc is a time constant. Now what is the role of this time constant? Role of the time constant. So this tau, which is given by rc, is a time constant. It controls how fast the stored peak decays. It controls how fast the stored peak decays. Now just a second. So this time constant controls how fast the peak decays. But in EMI EMC, this EMI EMC testing, so this electromagnetic interference testing, it can be either conducted or radiated emissions. Conducted or radiated emissions. Regulatory standards such as IEC or CISPR, they states that the EMI peak detector should respond quickly to fast transient spikes, but it should not store old peaks for a long time. This regulatory body states that the EMI peak detector should respond quickly to fast transients. So these fast transient spikes which happens for a very short duration of time, it should able to respond for them. So the capacitor should be able to discharge quickly, should respond quickly to fast transient spikes, but it should not store old peaks for a long time. But it should not old peaks for a long time. Otherwise, what will happen is a single spike would keep the output high and multiple spikes could not be distinguished. So if the if the time period is long, a single spike would keep the output high and multiple spikes could not be distinguished. What will happen then? If the time constant is not small enough, a single spike would keep the output high and multiple spikes could not be distinguished. And multiple spikes could not be distinguished. So capacitor must discharge fast enough before the next spike. So the capacitor should discharge fast enough before the next spike. So in the given question, this time period T is period between the spikes, not the time period of the signal. It's the period between spikes. So we want a capacitor to discharge before the next spike. So in EMI EMC, our aim in using the peak detector is to detect these spikes. So we want capacitor to discharge before next spike. This means, so this time period should be much greater than the time constant of the circuit. That means if it is much larger, that means peaks are coming after the capacitor is discharged completely. Then our peak detector will be able to detect the spikes. So that's why the correct option for this question was option A. If this question was not in terms of EMI EMC, definitely we want the time period to be much smaller than the time constant. But here our aim is to find these spikes, not just the peak. of the regular signal. We need to find out these spikes. That's why in the problem the correct option is option A. I hope this is clear. If you have any doubt in this question, please let me know. We can discuss it further. If it is clear, then we can move to the next problem. So this is the question 1 for our session, and that question that we discussed earlier was from the previous week session. So now let's start with question number 1. A half wave dipole carries a 200 megahertz current whose magnitude. Now one important thing is, so whatever the questions that have been discussed in the class, in the lectures, all are VM or IM, means that maximum value of the signal. But now this is that magnitude is given as RMS. So RMS is VM by root 2, or if it is current, it is IM by root 2. Since it is current, so this is what RMS current is. IRMS is IM by root 2. So that's what this RMS magnitude is given. At the center, a half wave dipole carries a 200 megahertz current whose magnitude at the center of the dipole, magnitude of the center of the dipole in the sense the excitation point, a current of 200 milliamperes is flowing. Then the total power radiated by the dipole and the electric field at a distance of 2000 meters away broadside to the antenna are. So first thing to notice is we have given a half wave dipole, and then in the problem they are asking us to find out the radiated power and the maximum electric field in the broadside direction, that is theta is 90 degrees. So for a half wave dipole, antenna, the total radiated power is given by E rad is 73 into IM by 2, IM square by 2. Now one thing to notice is this peak value of the current, but in the problem we are given, we have this RMS value IM by root 2, and from where this 73 comes is, this is the radiation resistance of a half wave dipole. So these are the some values that you should remember. What is the radiation resistance of a half wave dipole antenna is? It's always 73 ohms. Otherwise this formula is a basic formula. What is Ri square by 2, something like this, right? So P is equals to Vi, V is equals to IR, so I square R, and this comes because of this is the peak value. If this I hope now it is clear, right? So that's why this R is here is radiation resistance is 73 ohms. That's why I have written this formula directly. And in the problem we don't have this IM value, we have IRMS value. So simply, which is IM by root 2. So I can write this as 73 I in RMS magnitude square, because this IRMS is IM by root 2. So if in terms of IM, if I want to write is, then it will be root 2 times of IRMS, and when I take a square of root 2, it is 2, then that's why this 2 is gone. So the final formula in terms of IRMS is 73 times I in RMS whole square. Now everything else is given in the problem. We know what IRMS is. It is 200 milliamperes. So now just have to put the values. P radiated is 73 times So in the problem IRMS is given as 200 milliamperes whole square, and when we solve this we will get 2.92 watts. So this is the radiated power. So this is part 1 of the problem. Also they have asked us to find out the electric field at a distance of 200 meters away broadside to the antenna. So in broadside direction the electric field will be maximum. In broadside direction, that is theta is 90 degree, the electric field will be maximum. Therefore I can write the magnitude of this E max as 60 Im by R. So since we don't have Im, we have IRMS, so this we can write it as 200 into 10 to the power minus 3 multiplied with under root 2 divided by the distance at 2000 meters away. So R is 2000 meters. And when we solve this we will get 8.5 millivolt per meter. So this is the magnitude of the electric field along the broadside direction of the antenna. And if you match the given options, correct option will be option A, because the radiated power is 2.92 watts and electric field at a distance of 2000 meters away broadside to the antenna is 8.5 millivolt per meter. So I hope this question is clear. If you have any doubt in question number 1, please let me know. I hope you guys are also solving along with me. You can have a pen and paper and try to solve. If you want me to go slower, I can also pause in between starting the next problem. So I can give you some time to solve the problem if you want that. Or if it is fine in the current way, I can continue solving the problem and I can ask you for the doubt. Whichever is fine with you, please let me know. We can do whichever you like. So for question number 2, a dipole whose length is 3 by 2 wavelength, the pattern factor f theta becomes. So now we have to find the pattern factor for a dipole whose length is given as 3 lambda by 2. So this is simple question only, because we know what is the formula for the pattern factor. The pattern factor, that is f theta, is given by f theta is equals to, it's given by this formula, cos beta naught L by 2 cos theta minus cos beta naught L by 2 divided by sin theta. So this is the formula for the pattern factor for a dipole. Now in the problem, and also we know what is b theta. It's given by 2 pi by lambda or lambda naught. Now this f theta is given by, we can substitute the f theta beta naught value here, and also we know what is the L. So first I will substitute the value for beta naught, which is 2 pi by lambda. So this is L by 2 and 2 pi by lambda, so we will get pi L by lambda naught into cos theta minus cos pi L by lambda naught divided by sin theta. Now for dipole, whose length is 3 by 2 wavelength, that is L is 3 lambda naught by 2. The pattern factor becomes f theta is equals to, so I'm just substituting this L with 3 lambda naught by 2. So when we do that, we will get 3 lambda naught divided by lambda naught into 2 cos theta minus cos 3 lambda naught by 2 lambda naught, and here in denominator it is sin theta. Now this will become cos 3 pi by 2 into cos theta minus cos 3 pi by 2, and we know 3 pi by 2 is 0, cos 3 pi by 2 is 0. So this is sin theta. So our f theta becomes cos 3 pi by 2 into cos theta divided by sin theta. So this is the required pattern factor for the given dipole antenna whose length is 3 lambda by 2. Now we will match with the given options. The correct option here is option B. So this is the solution for question number 2. If you have any doubt in question number 2, please let me know. Okay, now we will go through question number 3. If anybody knows the solution for question number 3, can you please, if you know it, you can type in the chat also. So question 3 is the maximum radiations due to differential mode current is dependent on 4 things are given, and it's asking what is the maximum radiation due to differential mode current depends on. First is frequency of operation, second differential mode current, separation between the wires, fourth is length of the wires. So I hope everybody knows the answer for this one. So first we can start with writing what is the ED max, that is the maximum radiation due to the differential mode current. ED max, which is given by 1.316 into 10 to the power minus 14 into F square ID, there is a differential mode current, L is length of the wire, S is the separation between the wires, and divided by D, and D is the distance, like the distance between the observation point and the wire. So here F is the frequency, operating frequency, this is frequency. ID is the magnitude of the differential mode current, L is length of the wire, and S is the separation between the wires. Now since you have the formula which gives the dependence of this maximum radiation due to differential mode current, So it depends on frequency of operation, ID, L and S. Now I hope everybody got the answer, right? What will be the answer? Yeah, option 4, exactly. That is correct. It depends on all four of them. We can see it in this equation here itself. It depends on frequency of operation, yes. Differential mode current, yes. Separation between the wires means this S, yes, it depends on that, and also on the length of the wire. So the correct option will be option D. So this is a solution for question number 3. I hope everybody understood it.
Hello.
Yes.
Sir, we are unable to hear your voice.
Hello, am I audible to everyone else? Can anybody please respond? Vivek, everyone else is able to understand, everybody else is able to hear me. आपका माइक वगैरह आप अपने वॉल्यूम बढ़ा लीजिए ना. You can do one thing, you can just either increase the volume of your speakers or headphones. हाँ, क्योंकि बाकी सब लोगों को तो सुन रहा है. हेलो विवेक. Everyone else can hear me. So, hello, can you hear me, Vivek, now? Am I audible? Okay, yeah, you can try to rejoin. Okay. So, and for everyone else, I hope everybody else understood what is the solution for question number 3. Now we will move on to question number 4. So, yeah, can you hear me now? Am I audible, Vivek?
Yes, now audible.
Okay. So now we will move on to question number 4. For a current probe, the transfer impedance is given as 12 dB ohm for 10 to 100 megahertz. So it depends on this transfer impedance, depends on, for a current probe it depends on the frequency range, and for this particular current probe it is given as 12 dB ohm for 10 to 100 megahertz. If the probe voltage measured using a spectrum analyzer is given by, now whatever the voltage that current probe is getting is measured using a spectrum analyzer, and it is giving a value of 90 microvolt, then the common mode current measured in the current probe is. So we are using these current probes to find out what is the common mode current or differential mode current, current flowing through a wire. So now in the problem we have to find out what is the current measured in the current probe, because we have given the transfer impedance and the voltage measured using the spectrum analyzer. We have to find out what is the common mode current. So for this also one formula is has been discussed by the professor, which is given by, we know the formula already, we know the voltage reading by the spectrum analyzer. If we denote it as in dB microvolt, it is sum of the current value, which is will be in dB microampere, plus the transfer impedance ZT, the transfer impedance of that current probe for that particular frequency range, which is in dB ohms. So if you see this formula, we can now easily find it out, because in the question this voltage measured using a spectrum analyzer is given, and the transfer impedance is also given. Now we just have to find this thing. So we can easily find now what this will be. dB microampere, it will be so now one thing is there in the formula, we need it into dB microvolt, but in the problem this voltage measured is given as 90 microvolt. So if we convert into dB microvolt, it will be 39.08949 dB microvolt. Now I can directly substitute it here. So it will be 39.0849 minus 12. This is the transfer impedance dB ohms, and when we solve this we will get 27.0849 dB microampere. And if you match it with the given option, the correct option here is okay. Another thing is, all the options are given as microamperes, not in dB microampere, so again we have to convert it. So we'll move on to the next page. So what is here is, our solution is in dB microampere, which is 27.0849. Now if we convert it into microampere, we will get this magnitude of this common mode current is 22.6 microamperes. Now if we match it with the given option, the correct option here will be 22.6. okay, so the correct option is option number C. I hope question number 4 is clear. If it is clear, then we will move on to question number 5. If we consider a ribbon cable constructed of 28 gauge wires separated at a distance of 50 mils. So I think everyone has gone through the lectures. So these are some standard units which are like not the scientific units, but these are the units which are being used in the industry. So gauge is a unit of the diameter of that cable, and 50 mils is a 50 mils is the separation distance between the two cables. So it's a two wire cable, like a two wire transmission line, we can think it as in that terms. And the difference between the separation distance is given in 50 mils. 50 mils is around 0.016 inches. I'm not sure of that. So first we will convert and then we will. Okay, so if the ribbon cable constructed of 28 gauges wire separated a distance of 50 mils having length 2 meter and carrying 30 megahertz common mode current, the level of common mode current that will give a radiated emission broadside to the cable means the worst case that equal to the FCC limit class B limit of 40 dB microvolt per meter at 30 megahertz is. So one thing that we should remember always, it won't be given in the problem at all the time, that is FCC class B measurement distance is always is 3 meters. So here our D is given as 3 meters. And what we have to find it is in the problem is the level of common mode current which can give a maximum E field or maximum radiated field of 40 dB microvolt per meter. So we have already solved something similar here, right? Okay, we didn't solve it for the common mode, we solved it for differential mode. So the formula for the common mode is, I will write down it as so the level of the common mode current EC max is given by 1.257 into 10 to the power minus 6 magnitude of this IC into frequency into length of the wire and divided by the distance d. So in the problem d is not given, but the thing that is given is FCC class B limit, and the measurement distance is always 3 meters, so that's why we have the d also now. And length is given, and this EC max does not depend on the separation distance, that's why I'm not using the S here. So if you think clearly, this some of the information which is given is kind of useless for us. So if you don't even know the conversion of 28 gauges into meters and this 50 mils into meter, it doesn't matter because we are not using the separation distance in the formula itself. So when we solve this, now we have to find everything is known. EC max is also known. It is given as 40 dB microvolt per meter. The only thing that we have to do now is we have to convert this, because in this formula it is not in dB, it is in real units like volt per meter. So when we convert it into volt per meter, we will get 100 microvolt per meter. So we will substitute it here. 100 microvolt per meter is equals to 1.257 into 10 to the power minus 6. IC is unknown. Frequency is given as 30 megahertz. 13 to 10 to the power 6. Length of the cable is given as 2 meter, and the distance of the measurement is 3 meters. Now we can easily solve for IC. So IC is given by, when we solve it, we will get 3.98 into 10 to the power minus 6 amperes, or I can write it as 3.98 microamperes. When we match it with the given option, the correct option is option number C. Sorry, option number B, because the answer is 3.98, right? So the correct option is option number B. I hope question number 5 is clear. If you have any doubt in this, please let me know. So if this is clear, we will move on to the next problem. So here for question number 6, 7 and 8, data is common. So whatever this 2-wire cable is there is common for question number 6, 7 and 8. So here it is given as the currents in a 2-wire cable at 100 megahertz are measured, giving values as shown in the figure. Okay, so they have given us I1 and I2, and we don't know if it is common mode or differential mode or sum of the both. Only thing is given as this is given. Maybe they have used some kind of a current probe to measure the currents, and the currents are given as 104 milliamperes in the wire 2, and in wire 1 it is 96 milliamperes. And the length is also given. L is given as 2 meters, and the separation distance is 5 centimeters. Okay, so this is the common data for all the problems. Now we will move on to question number 6. Keeping all other parameters same, if the separation distance between the two wires is increased 4 times, then the magnitude of the maximum radiation due to common mode component of the currents. Maximum radiation due to the common mode component of the current. 4 options are given. What will happen? So question is saying that what will happen if the separation distance between the wire is increased by 4 times. So they are asking, what if we make it 5 centimeter as 20 centimeters, increase it by 4 times, right? What will happen to the maximum radiation? So I will note down the formula here. Due to the common mode, EC max is given as 1.257 into 10 to the power minus 6 common mode current into frequency into L by D. Now can anybody tell me the answer here? You have the formula. if you see, there is no dependence on S, right? If you know the answer, you can just comment it. So what they are asking is, what will happen to this EC max when we increase the S by 4 times? What if we make it 20 centimeters? What will happen to EC max? Will it increase by 4 times? Will it decrease by 4 times? Or it remains the same? Or option D says increase by 16 times. You understand the problem, right? Correct. Option C, it remains the same. Because if you see, there is no dependence on S for EC max. If it has been asking about the maximum radiation due to the differential mode current, then the answer could have been different. But the maximum radiation due to the common mode component of the current does not depend on the separation distance between the wires. So that's why this correct option is option C. It remains the same. So the maximum radiation due to common mode current does not depend on the separation between the wires. So the correct option is C. Now we will move on to question number 7. Same wires, same current, same separation distance and length. Now if the magnitude of the maximum radiated emission due to the common mode component of the current at 10 meter is, so EC max is given as 110 dB microvolt per meter at 10 meters. Then the length of the wire is, now we have to find the length. So what is given in the problem is F is 100 megahertz. So from this F we can find what lambda will be, C by F, which is 3 into 10 to the power 8 divided by 10 to the power 8, because it is 100 megahertz. So the wavelength is 3 meters, and I1 is given as I1 is given already in the problem as 104 milliamperes, and I2 is given as 96 milliamperes. And if you observe, they are moving in the opposite direction. I2 is moving from left to right, and wire 2, I2 is moving in right to left. So space is not there. I will move on to the next page. So the direction of I2 is opposite to that of I1. So a negative sign is used with I2 here. So what I am saying is, I am taking I2 as minus 96 milliamperes just because the direction is opposite to that of I1. So now we know how to find out IC, the common mode current, if I1 and I2 is given, which is given by this formula, I1 plus I2. So the direction is opposite, that's why I am putting a negative sign here, divided by 2. And when we solve this, we will get 4 milliamperes. Now in the problem, S is given as 5 centimeters, or it should be in meters, so I am writing it as 0.05 meters, and the observation point is at 10 meters away. So now we have to find out the length of the cable, and we also know what is EC max. EC max is given as 110 dB microvolt per meter. but the formula that we have derived is in volts per meter, so I will convert it into volt per meter, and it comes out to be 0.3162 volt per meter. Now I can directly use the formula for EC max that we have already used in the other problems, right? So EC max is 0.3162 is equals to 1.257 into 10 to the power minus 6 into IC F is the frequency L. This L is only unknown that we have to find, and D. So when we solve this, we will get 0.3162 is equals to 1.257 into 4 into L into 10 to the power minus 1, and the distance of the measurement is at 10 meters. So I can rewrite this as 1.257 into 4 by 100. I can take this 10 to the power minus 1 in the denominator, right, and multiplied with L. So L is given by 0.3162 into 100 divided by 5.028, and when we solve this we will get 6.288 meters. So this will be the length of the wire when we are getting a maximum radiated emission of 110 dB microvolt per meter at a 10 meter distance. So that will be the wire length L. So if you match it with the given option, the correct option is option D, 6.3 meters. I hope this question is clear. If you have any doubt in this, please let me know. If this is clear, we will move on to question number 8. The currents in a two-wire cable. Okay, this is the same data. Now question 8 is, keeping all the parameters same, if the operating frequency is increased by 3 times, then what will happen? So what is it's asking is, increase the operating frequency by 3 times, and what will be the effect on the radiated emission due to common mode currents and due to differential mode currents. Okay, we know one thing. We know that ED max. So guys, one more important thing is, you have to remember ED max and EC max formulas. So is directly proportional to F square, ED max, and EC max is directly proportional to F, not the square, only F. EC max is directly proportional to F. Now we can just go through the options. Now we know the dependence of ED max, the radiated emission due to differential mode current and common mode current, is given here. Now the option A says, what we have done is we have increased the operating frequency by 3 times. The radiated emission due to common mode current increases by 3 times, and due to differential mode current increases by 6 times. So in option A, the first part is correct. The common mode current is increased by 3 times because it's directly proportional to F. But in differential mode current, the radiated emission will not increase by 6 times. It will increase by 3 square, means 9 times. So the correct option, if we see, is option B. The radiated emission due to the common mode current increases by 3 times, and the radiated emission due to differential mode current increases by 9 times. So the correct option here is B. If you have any doubt in this, please let me know. If this is clear, we will move on to question number 9. In question number 9, two statements are given. Statement 1 states that the level of common mode current can be reduced by lowering the pulse train frequency while differential mode current remains unaffected. And statement 2 states that reducing the pulse repetition rate moves the breakpoints of the pulse spectrum lower in frequency. Now we just have to comment, and the options are asking if both the statements are correct or only statement 1 is correct and statement 2 is false, or option C says option 1 is correct but statement 2 is false, and option D says statement 1 is false but statement 2 is true. So for common mode and differential mode currents, the current level can be reduced by slowing the pulse rise or fall time, or we can do the pulse repetition rate. We can reduce the pulse repetition rate, reducing the pulse train frequency. Since these will move the two breakpoints, the breakpoints was 1 by pi tau and 1 by pi tau r, right? These were the breakpoints. So these will move the two breakpoints of the pulse spectrum lower in frequency, causing the spectrum to roll off at a faster rate at this frequency. So statement 2 is correct. Reducing the pulse repetition rate moves the breakpoints of the pulse spectrum lower in frequency. So I will note it down here. For both common mode and differential mode currents, the current level can be reduced by slowing the pulse rise and fall time. Can be reduced by slowing the pulse rise or fall time. So if you read the statement 1 states that the level of common mode current can be reduced by lowering the pulse train frequency, while differential mode current remains unaffected. So part 2 of this statement 1 is not correct, because for both common mode and differential mode currents, the current level can be reduced by slowing the frequency rise and fall time, means lowering the frequency. Since these will move to the breakpoints of that 1 by tau r and 1 by tau of the pulse spectrum lower in frequency, causing the spectrum to roll off at a faster rate at this frequency. Option statement. So statement 2 is correct but statement 1 is not correct, because both common and differential mode currents can be reduced by lowering the pulse train frequency. So if we go through the option, the correct option is option D. I hope question number 9 is clear. Now we will move on to question number 10. Question number 10. Consider a 3-meter cable and a current probe with a probe voltage of 20 dB microvolt. In order to comply with the FCC Class B radiated emission limit at 500 megahertz of 30 dB microvolt per meter, the transfer impedance will be. So everything else is given, we just have to find the ZT. And in this problem at least D is given. Otherwise, if it is not given, if one thing is given as FCC Class B radiated emission limit, then we have to assume D is 3 meters, but already it is given in the problem. So we know that EC max is given by 6.28 into 10 to the power minus 7 voltage reading by the spectrum analyzer into frequency into the length divided by the transfer impedance into the distance of the observation point. So now everything is given in decibels, so it's better to convert everything in dB. So converting this to dB and solving for the transfer, impedance gives so I'm just directly writing the formula. First what we have done is we have converted into dB, means I've taken the logarithm, and then I'm writing, and since everything here is in multiplication, so in log it will become in addition. So Z T in dB ohms is given by voltage reading from the spectrum analyzer, which will be in dB microvolt plus 20 log 10 of frequency plus 20 log base 10 of length. Since these were in denominator, so minus 20 log 10 of distance d, and minus EC max, which will be in dB microvolt per meter. And when we take logarithm of this quantity, we will get minus 4.041. So when we solve this, we get 20. It's already given. We voltage the voltage probe of 20 dB microvolt, so it's in 20 plus 20 log of 500 megahertz, 20 log 10 of 500, this already is in megahertz, plus 20 log length is 3 minus d is also given as 3 meters, so 20 log 3, so this will get cancelled out, and minus this is 50 dB microvolt per meter, so EC max is 50, and minus 4.041. So we'll move on to the next page. So when we solve this, we will get the transfer impedance in dB ohms as 20 plus 53.98 minus 50 minus 4.041, and when we solve this, we will get 19.939 in dB ohm. So this is approximately, because options are not in a rational number, so it's given as an integer, it's a whole number, so 10, 15, so the nearest whole number is 20 dB microohms. So when we match it with the given option, the correct option is option A. I hope this is clear. If you have any doubt in question number 10, please let me know. So if there are no doubts, this is all for today's session. If you have any doubt, you can also email me to my email ID. I will note it down here. So I will suggest you guys to uh, spend some time while solving the assignment, because assignments are also important and they carry a lot of marks. So, and assignment problems are easy. If you solve all of them, and just go through once the assignment due date is over. So by the next week there will be assignment solutions also will be released. So I request you to go through them also once you are done with the assignment, so that you can find out how to solve the question, what are the problems that you have made in the previous assignment, because the questions will be similar in the final exam also. So I'm talking about if you are trying to give the exam, if you have registered for the final exam for this course, it will be a good idea to solve all the assignment problems, and the problems which are being discussed here, those also will be helpful because they are also pretty similar to what are the assignment problems are. So this is all for today's session. We will meet in the next week. Thank you. Thanks for joining.